Hello guys, welcome back. This is lecture 15 of the lecture series Signals and Systems. In this video, we'll be seeing about discrete time systems and we'll see the properties of discrete time systems including memoryless, invertibility, causality, stability, time invariance and linearity. So let's get started. So in the previous video, we saw about discrete time signals. In this video, we'll start with discrete time systems. So discrete time systems are nothing but systems which transforms discrete time signals into another discrete time signals. Basically, transformation of x of n to another discrete time signal y of n, and the system comes in between. So discrete time systems transforms discrete time inputs to discrete time outputs. Okay, so we'll see the properties of the discrete time systems. So based on the properties, how they are classified. So this will again be a repeat as a review as we saw it for the continuous time case. So the first property we are seeing is the memoryless property. So a system is said to be memoryless if the output for each value of the independent variable is dependent only on the input at the same time. Okay, so what it means is your y of n, if it is only function of x of n and not function of x of n minus n naught for n naught not equal to 0. Okay, in that case, we can say the system is memoryless. So examples. So you can have many examples. So the square function is also an example because y of n is depending only on x of n. Okay, so which is not memoryless? Example for that is, you just write x of n minus 1 or any constant, right? It will not be memoryless. So such systems are said to have memory. Okay, so the second property we'll see is invertibility. So a system is said to be invertible if distinct inputs gives distinct outputs. So why this is necessary? Because we want to map it, right? So you have all the inputs here and you have all the outputs. And we know that a system is nothing but is similar to a function between inputs and outputs. So you have some kind of mapping from here to here. right? A mapping. And if that mapping is 1 to 1 and on to, which also means for each distinct inputs, you have distinct outputs, then the system is invertible and it has an inverse, right? So what will be the inverse function with these as inputs and this as outputs? The relation will be the inverse function or inverse system, right? We'll see some examples. Here y of n is equal to 2x of n. So let's say this is system 1. Okay. I want to find inverse of the system. So first we should observe that each input gives distinct outputs, right? So if I take a system S2, then I'll define its function. So let me take w of n is equal to some half into the input. Let me call it u of n. So this is the output and this is the input for the second function. So second system. So here again, if you see S2 of S1, it will be nothing but w of n is equal to half of y of n, which is nothing but half into 2 of x of n, so which is equal to x of n. So if you have two systems and if you pass S1 and S2 and if you have the signal x of n and you get the same signal x of n outside, then S1 and S2 are said to be inverse of each other. So this is basic mathematics, right? You should have learned it in functions. Okay. So this is with the invertibility property. So the next property is the causality. So what does causality means? Any output, it depends only on the previous inputs and not on the future inputs, right? So a system is said to be causal if the output at any time depends only on values of the input at the present or in the past. Can be and also, right? So or and in the past and not in the future. So what examples can you think of? So y of n equal to x of n minus 1 plus x of n minus 2, right? Or you can have y of n equal to summation, let's say k equal to minus infinity to 0 x of n minus k. It should be n plus k, right? Or you can take it from 0 to infinity and use n minus k. So it is still causal because it is depending on the present input and all the previous inputs, right? So these are causal systems. So non-causal systems, they depend on future values also, right? So your y of n is equal to x of n plus 1. It is a simple example. So you can have n number of examples. So that is all with causality. So let us now take a look at stability. So a system is said to be stable if bounded inputs leads to bounded outputs. So this is also called as BIBO stability, right? So if you have a system and you give some bounded input, so your x of n, so you say x of n is less than some b, some constant b, okay? Then your output y of n should also be bounded, which means your output should also be less than some number which depends on b or may not depend on b, and that should be less than infinity. So in this case, the system can be said as stable. If bounded input leads to unbounded output, then we can say the system is unstable. So let us see some examples. So first example, we'll take y1 of n is equal to e power x1 of n. So now what we can see, let's first assume x1 of n is bounded. So what about your y1 of n? So it is equal to mod e power x1 of n. So this we can say it should be less than e power mod x1 of n, less than or equal to. And again, using this criterion, this inequality, this will be e power less than e power b. So your y1 of n is also less than some k less than infinity. So it is stable, right? This function is stable. The system is stable. So we'll see an example for instability. So y2 of n is equal to t x2 of n. Okay. So what happens here? Let's say our x2 of n is bounded. So what happens to our y2 of n? So we'll get mod t x2 of n. So this will be less than or equal to t mod t into mod of x2 of n. Again, this is less than or equal to mod t less than b, or strictly less than, right? But this may not be less than infinity because t itself tends to infinity, right? So your y2 of n tends to infinity as t tends to infinity. Hence, this system is unstable. Why? Because it is growing unboundedly, even for a bounded input. Hence, it is not a stable system. So our next property is the time invariance property. So here what do we have? Let's say if y of n is the output of a system with input x of n, then for an time invariant system, y of n minus n naught should be the output for the input x of n minus n naught, right? So if your input is shifted in time, then your output should also be shifted in time by the same amount. That is what it means. So let us see some examples. So let's say your y of n is equal to cos of x of n. So for x of n, I got the output as cos of x of n, right? For x of n minus n naught, what will I get? I'll get it as cos of x of n minus n naught. And hence this is equal to y of n minus n naught, right? So we need to understand how these two are different, right? So when this is happening, it means that you are replacing x of n with x of n minus n naught, right? And here what is happening, this equal to, I'll use a different color. This equal to is nothing but you're replacing n with n minus n naught, right? Where are you replacing it? Here this is y of n, right? This one or this one, right? So here you're replacing n with n minus n naught. So these two conditions, when you do it two different ways, if your final result is same, then it means the system is time invariant. If they are different, then they are not time invariant. So let us take another example. So let's say your y of n is equal to nx of n. So let's do the first method, replacing x of n with x of n minus n naught. So this is the response you will get, actual response you will get for the system. So which is nothing but your y of n or y dash of n is n into x of n minus n naught. So secondly, replacing n with n minus n naught. So this is the response we would have got if the system was time invariant, correct? From the definition, this applies. So what will our, let's say this y double prime of n, or this is just nothing but y of n minus n naught, is n minus n naught into x of n minus n naught. So clearly y prime of n is not equal to y of n minus n naught. So this system is time variant or time varying, right? It's not time invariant, it is time varying. Okay, so our last property will be linearity. So linearity and the time invariance property are most important, and that's how we get the LTI systems, right? Which we'll be discussing next. So these are very important. So in linearity, what do we call as a linear system? A linear system is a system that has a property of superposition. So what does superposition mean? So let's say we have inputs x1 of n up to, let's say, xm of n, and they all give outputs y1 of n to ym of n. Then if we have the weighted sum of these inputs, let's say a1 x1 of n plus a2 x2 of n plus am xm of n. So if we give this as input, and if we also get the outputs as weighted sum of these outputs, which is nothing but a1 y1 of n plus a2 y2 of n, and so on up to am ym of n. Ym of n. So if this is true, then we can say the system is linear, and this property is called as the superposition, right? So the statement goes as this: if the weighted sum of inputs is equal to the weighted sum of respective outputs, right? x1 gives y1, x2 gives y2, and this property is superposition property, and the system which is satisfying this is called as the linear system. So the superposition property can be broken down into two. So the first one is the additivity property. it states that if x1 of n gives y1 of n and x2 of n gives y2 of n, then x1 of n plus x2 of n should give me y1 of n plus y2 of n. So this is your additivity property. But this alone is not enough. You also need the property of homogeneity. This is also called as the scaling property. So if you have x1 of n giving y1 of n, then ax1 of n should give you, what should it give you? It should give you ay1 of n. So here a can be a complex number. Okay. So one important fact to notice for a linear system is that linear system, zero input should give zero output, right? So why is this necessary? So if your zero input doesn't give zero output, let's say it gives some output B, then if I scale this input, then my output also will scale, right? As per linearity, my output also should scale. But if you see, this is nothing but 0. So 0 gives A into B. So this is a contradiction. Same input cannot give two different outputs, right? Because of the properties of function. So contradiction. So hence, this is true. Zero input should always give zero output. Okay. So let us see some examples. So first we'll see for a non-linear system. So it is very simple. Whole square, right? Let's say x of n whole square. Then what happens? Let's first check the additivity property. So here x1 of n will give me y1 of n, which is nothing but x1 of n whole square. And my x2 of n will give me y2 of n, which will give me x2 of n whole square. So my x1 of n plus x2 of n gives me x1 of n plus x2 of n whole square, which is equal to x1 of n square plus x2 of n square plus 2x1 of n into x2 of n. So because of this extra terms, this is clearly not equal to y1 of n plus y2 of n. So this is not linear. This is a non-linear system. So this is our first example, and this is straightforward because you have the square term. But if you also check for this y of n equal to x of n plus 1. At first you may try to conclude that it is a linear system, but it is not linear. Why? Because x of n equal to 0, it gives y of n equal to 1. So zero input is not giving zero output here. So then this system is also non-linear. Okay. So can you think of a system which is linear then? So if it is some k times x of n, then this system is linear. Yes. So let us check the additivity and the homogeneity property. So x1 of n gives y1 of n equal to kx1 of n, and my x2 of n gives y2 of n equal to kx2 of n. So my x1 of n plus x2 of n, it is gonna give me k into x1 of n plus x2 of n. And this we can write it as kx1 of n plus kx2 of n. And this is nothing but y1 of n plus y2 of n. So additivity property is okay. What about homogeneity? My ax2 of n gives me k into ax2 of n. Anything, it can be x1 or x2. Okay. So this I can write it as a into kx1 of n. So which is nothing but ay1 of n. So my homogeneity is also okay. So this system is a linear system. Okay. So that is all with the discrete time systems properties. In the next video, we will take a look at the LTI systems, which are nothing but linear and time invariant system in more detail. Until then, stay tuned. Take care. Bye-bye.